and welcome to another episode of Bevy Basics. In this episode, we'll be looking at a relatively new and obscure feature of Bevy. This is observers. To be honest, observers are probably the first time that I'm making one of these videos when I'm not entirely confident I understand the concept to the level that I would normally when I make one of these videos. As I'm having so much trouble tracking down any information about observers, I figured that at the very least, I would have people in the comments telling me what I got wrong and other information that I may not have known about observers. And worst case scenario, this video can be a confident repository for all the information that I currently know about observers for anyone looking to find the information out themselves without having to dig through lots of source code and comments and changes to Bevy over the updates. So let's start with what are observers. Observers are a special type of system that take a trigger as their first parameter. They can then have any other system parameters like a normal system would. Unlike a regular system that you add to a scheduler in your application that then works out when to execute the system based on the schedule rules implicit from the parameters or explicit from run conditions, observers must be triggered explicitly. This is done with world access to run the observer immediately or using commands to have an observer run in the next command flush. Observers can recursively trigger themselves or other observers using commands, as all commands will be flushed before moving on to the next frame. This includes commands that were added after the current flush has started. Observers are a push style of event processing that were first introduced in 0.14. They're added for when Bevy's existing pull style reaction processing falls short and can be used in conjunction with lifestyle hooks, also added in 0.14 to create robust bookkeeping systems like Bevy's hierarchy. Before observers were added, if you wanted to build a reactive system in Bevy, whether you were responding to an event or detecting a change in the ECS world, you only had access to pull-based mechanisms like event readers and change detection queries. They are considered pull because they will fetch or pull the relevant data when they are run. This is great for when you are processing lots of data, since all of the data can be fetched simultaneously for a fixed overhead. But that overhead is paid regardless if any information is actually fetched, which wastes compute when you're using it on events that are triggered rarely. There's also a risk that events can be missed entirely if a system doesn't run at least once every other frame. In practice, this isn't a big deal. Most systems run every frame. This does mean that if you want to guarantee that you never miss an event, your system has to run continuously, which adds overhead even if it might not be doing anything useful. Bevy uses a double buffer to store events, allowing systems that run in earlier stages to respond to events sent in later stages on the next frame. This is done by storing new events in the B buffer that is then swapped with the A buffer the next time events are updated. And then the B buffer is cleared, meaning that you have a copy of all the events sent in the previous frame and then all the events that are have currently been sent this frame, allowing for systems to run in a different order and still respond to all events. This issue doesn't exist with change detection, or it does, but like in a much nicher case, since Bevy relies on a tick system. It works by comparing the tick a system last ran with the tick when a component was added or modified, meaning change detection will find any component that has been added or changed since the last time that system ran. So it's much easier to have change detection systems run less frequently without missing anything, but not impossible, because Bevy does have a max change age. Any change older than this when a system runs will not be considered to have changed. But don't worry, this maximum is something like 6+ hours at 1,000 ticks per frame and 144 frames per second. So not something you really need to consider unless you're planning on having a system that only runs like once every 6 hours. I don't really know how ticks are counted, since even my simple Tetris game has almost 400 ticks per frame. So it's possible that a lot of ticks could accrue in complex games, since it appears that it's something like once per system run is actually considered a tick, regardless of how many systems are run in a frame, which does mean that very complicated games may shorten this time considerably. So a bigger limitation of the change detection beyond the maximum age is actually that you can only detect that a change happens and not necessarily process every single change as it happens. That's because change detection doesn't tell you what changed or how many times it has changed, or, funnily enough, even if it's actually changed at all, just that something dereferenced a mute into its inner value since the last time the system ran. So if you need to compare before and after values or do bookkeeping across changes, that's where you need to use component hooks. I've got a video about these, so you can check that out after this one. Another downside is an inherent or potentially variable delay between when something happens and when something is to react to it. This delay comes from the pull-based nature of both events and change detection. For example, if an event is sent before the system that handles it runs during the frame, it gets processed in the same frame. But if the event is sent after the system has already run, it won't be handled until the next frame. And since Bevy's system execution order is non-deterministic unless you explicitly define it, This delay can be unpredictable and hard to reason about because it's even possible to have two events processed in the same frame. If the system that sends the event runs after the processing on one frame and before the processing in the next frame. You can control execution using the before and after constraints or using chain if you have the systems laid out in the order when adding them. Another option is to place systems in specific schedules like pre-update to ensure they run before others. But without that setup, the timing event handling becomes inconsistent and potentially problematic. But the biggest limitation by far is that you can only pull data once per system execution. This makes recursive behavior difficult. You can't create event-driven loops that run multiple times within a single frame. It is possible to have multiple instances of a system run in the same frame, but without creating a custom scheduler with the ability to dynamically determine the number of times it should run, you have a finite number of times the system will run in each frame, and a lot of overhead on systems that may not need to run each frame. Whereas observers have the ability to trigger themselves and or other observers, allowing for a chain of observers to be executed in a single frame. As you can see, there are a number of things that observers were added to address, but it's important to remember that observers were added to complement the other parts of Bevy, not to replace them. So make sure you're using the right tool for the job. Bevy is making sure you have access to a wide array of options when approaching a problem. So we should probably address how to use observers. That starts with the system parameter that makes them tick, trigger. So what is a trigger and how do they allow us to make observer systems? A trigger is a system parameter that wraps an event and is used to indicate that a system is an observer system rather than a normal one. Triggers are more restrictive than normal system parameters in that they can only have one trigger in a system and it must always be the first system parameter. The primary use of a trigger is to provide type data so that the compiler knows what the observer will want access to, and the metadata of the observer trigger to the system at runtime. The type data is used for all sorts of things, like working out what event will actually trigger the observer, as well as what components need to be watched. Bevy then type erases this to make observers more useful to end users, while maintaining the performance improvements from the static typing provided by the compiler. A trigger is made up of three parts. The first of these is generics. The E generic represents the event type. This tells Bevy what kind of event should trigger this observer and what data needs to be passed to it when it runs. The second generic, B, defines the target components, essentially what the observer is watching for. If B is set to the unit type, the observer is considered untargeted. That means it will respond to any trigger of the type E, unless it's scoped to a specific entity, in which case that entity must be triggered for the observer to run. If you assign a bundle to B, its components act as an OR-style match. If any of the components in the bundle are triggered, the observer will be triggered. However, if the observer is assigned to a specific entity, then the condition becomes more strict, effectively an AND-style match. In that case, the observer will only run if one of the entities it is watching is targeted, and at least one component from the bundle was targeted. The second part of the trigger is the data it provides to the observer system. This includes a mutable reference to the event that triggered the observer and a mutable Boolean flag that indicates whether the event should continue to bubble up through Bevy's event propagation path. In Bevy, each event type can specify a traversal type, which defines how it propagates. By default, this is just the unit type, which means that events don't propagate at all. But it can be set to something like child of, which tells Bevy to bubble the event up the entity hierarchy from child to parent, triggering all observers that watch for that event up the path. Because you have mutable access to both the event and the propagate flag, it's possible to modify the event as it propagates and stop propagating at any point by setting the flag to false. A good example of this would be a damage system with armor layers. As damage travels up through each armor entity, the event could reduce the damage value at each step. If it reaches the player's body, it will then be applied as HP loss, or if all damage was absorbed by a layer, it can then set the propagate flag to false, stopping the propagation of the damage further. The next part of a trigger is some runtime metadata provided through the observer trigger struct. This struct includes the entity that the observer is attached to, which is useful if you want to automatically despawn the observer after it runs or some condition is met. The component ID of the event that fired this run of the observer. Now this one is a bit mysterious to me, since the event type is already known using the generics when you define the observer in the first place. It's not immediately clear to me why you need to have access to the event type in the component ID here. My guess is that it's used internally by Bevy for some kind of type erased optimization, or maybe for working with the trigger in a context where this information isn't provided by a generic. Like I said at the beginning, observers are still kind of a black box, so if you know why an observer might need access to the event component ID that triggered it, and wouldn't otherwise know this from generics, please let me know. Another speculation I have is that an observer can watch more than one entity type somehow, despite Bevy saying you shouldn't do this. And it's possible that this is so that you know which event triggered this specific run of the observer. You also get a list of component IDs that cause the observer to be triggered. This will be one or more of the components defined in the B generic and will always be empty if it's a global observer and you've defined the unit type, since it's not possible for any component to trigger it. You also get access to the entity that was targeted by the event trigger. This is different to the entity that the observer is actually placed on and is instead the entity that the observer is watching. For global observers, this will always be entity placeholder, which is just the max value that an entity can set to, and Bevy uses when it wants to indicate that an entity has not actually been assigned. If the event is propagating, this will be the current entity along the propagation path, not the original entity that the event was targeting. And finally, there's a maybe location, which gives you access to the source location where the observer was created if you have track locations enabled. Otherwise, it's just a zero-sized type that the compiler will completely optimize away. Now we know how to write a system that can be used as an observer. Let's talk about how to actually spawn an observer into our application. As far as I'm aware, there are 3 ways to add observers. The most flexible is to manually spawn an observer. This is done by spawning a new entity with an observer component. You can make a new observer component by calling new and providing the observing system. You can then optionally chain calls of with entity and or with component to make the observer trigger with those entities and or components as targeted. It's also possible to provide an error handler that will be invoked if the observer throws an error. If you don't provide one, Bevy will simply use its default error handler. It's important to note that the entity that we actually spawn the observer on is not really the observer itself. This is slightly confusing by the fact that it's called an observer, but the way Bevy actually handles observers is when an observer component is added, it extracts all the information out of that component to spawn an actual observer in its internal structure. This may be changing in the future and why they're doing it this way, but it does mean that if you modify the observer component, these changes will not be reflected on the actual observer that runs. You can find this in a single note on the observer class. It says that when you call watch entity, because it takes a mutable reference, it's possible to call this easily on the observer component itself. And it says, note, if this is called after an observer is spawned, it will produce no effect. And the idea being that the observer's already been extracted out of the world and therefore modifying it won't do anything. This is not noted anywhere else that I've found, but yeah, it is important to note that you can't modify an observer once it's spawned. You'll have to despawn it and respawn an observer with the modified behavior. Bevy also has some rules about which entities can be observers, making an explicit note that observers should always be their own entities. So don't add the observer component to the entity that it is observing. Bevy has built-in logic to clean up observers, needing to clear out cached data and unwind a relationship between who is observing who. I'm not sure if this is why Bevy doesn't want observers watching themselves, as it could have issues in the cleanup logic or prevent the observer from being cleaned up at all, since it will never stop watching its final entity, since that entity is itself. But my best guess is that some kind of infinite loop that can happen when it's trying to follow the observed by relationship, since the entity that would be observed is itself and would be an infinite loop. The next way to spawn an observer is by using the add observer method on your app. Under the hood, this is functionally the same as spawning a new entity with an observer component, but without specifying an entity to watch. This creates what's known as a global observer. It listens for all events of its type and runs whenever one is triggered. However, if the observer's B parameter, the targeted components bundle, is set to something other than unit, the event will still need to target at least one of those components in order for the observer to be triggered. Now, the final way to create an observer is through the observe method, which can be called when spawning an entity or any time you have access to the commands for an entity. This sets up a local observer, automatically configuring it to watch the specific entity. This is a convenient shortcut for spawning an entity and attaching an observer that calls watch entity and targets the entity that you have access to, all in one step. Now we know how to write a system that can be used as an observer and how to spawn an observer into the application. But just for a bit of fun, let's take a peek behind the curtain. If you're curious about what makes observers tick under the hood, stick around. We're about to break down what actually inside an observer component, or if you're not into implementation details, feel free to skip ahead. I won't be offended. All right, let's F12 this sucker and take a look. The observer component itself is fairly straightforward. Again, this is mostly because Bevy extracts information and stores it elsewhere internally, so it's more just a sequence of configuration data that is then used somewhere else. There's also a lot of fancy stuff going on to do with type erasure. So first up is the system that the observer runs. This system is type erased. This means that Bevy strips away the type information and stores it in a form that can be handled dynamically, and the compiler will have to compile it in a special way. Because of this, Bevy has to do some extra work behind the scenes to make sure that the system only executes with the correct data provided to it. Next, there is the observer descriptor. This is where the observer watch configuration lives, including the event type, the components, and the entity that should be triggered. Now, this is another point that confuses me. Since Bevy's observer descriptor here takes a vector of component IDs instead of a singular component ID for its events. The reason this confuses me is Bevy explicitly states in a few places that the event ID must match the event that is in the generic type of the trigger. And therefore, having a vector in the observer's descriptor doesn't make sense, because that would imply that more than one type of event can trigger something that can only be triggered by one specific type. The only thing I can think of that this makes sense for is if ZSTs or zero size types are allowed, or potentially types that have the same data structure underneath but different IDs, and therefore multiple different events can trigger the same observer, and then the observer can work out which one it is actually using. But this seems incredibly dangerous, especially considering that anywhere you interact with this component ID is considered unsafe code, at least when you're setting it, because it's so important that the type here matches the type of the observer system. So it makes zero sense for this to be a vector. If you understand why Bevy is doing this, please do let me know, because it is like confusing me to no end. After that, we have the hook on add. This is a special function that runs when the observer is added to an entity. This is identical to an on add hook, but is through a layer of abstraction. This is where some of that type erasure voodoo comes in. Since when Bevy creates this hook on add function, it provides all the generic information to be able to create a system that can register the observer correctly, because it knows all the types ahead of time, and then erases the types on itself. And finally, we get the error handler. This is an optional function pointer you can provide to handle any errors that might occur when observer runs. If you don't set one, Bevy will just fall back to the default error handler. I feel like I'm missing like a whole chapter here, but this is all the information I have on observers, well, at least that I'm comfortable enough to put into the video and actually explain. There are some small amount of extra information that I uncovered. Things like how observers are stored and run, like observer state and the observer struct, that seem to have all their fields private and the same with their methods. So it doesn't seem like there's any way to actually interact with them outside of the engine development itself. This makes even less sense by the fact that there's an observer runner type that specifically declares that it is a type that is used to run observers and can be overwritten, but all one call to it in the source code is private, and therefore there is no way to override it, and like without like breaking unsafe rules. And even then, I don't think you can access private fields in unsafe. So there's no way to override the default observer running system. And so it doesn't make sense that they have a comment that specifically says you can override this for custom behavior when you cannot even access it, let alone override it. But maybe this is all things that will be added in the future, or potentially were part of like a pull request that got yoinked from 0.16 to in order to get it out in time. So like maybe functional but not finished, and therefore not added to the actual version. If I missed anything, do let me know again in the comments. And if this video gets like a whole bunch of influx about like how observers work and pieces I missed, and it's like, I'll remake the video and upload it like as part 2 or something, explaining all the details of observers that I missed. And let's hope that I didn't miss something major that changed with 0.16. I didn't notice anything when I was going through the source code, but that doesn't mean they didn't change something. If you're interested in watching an incredible video about Rust vec type or its global allocator, I highly recommend BehindBlueScreen videos on the topic. They're amazing, in-depth videos to like a level that I couldn't dream of. They're all like animated, and I'm assuming reanimated just because of that, like the flow of it, but it could be like any kind of animation software for code, because they all kind of do the same kind of code logic. But it's amazing. He's got like less than 1,000 subscribers, so like I figured I'll give him a shout out because the videos are like really interesting and like really in depth. Got to give the guy props for making these incredible videos. I hope you've all enjoyed the video. This video drained the shit out of my sanity. Like it took me way longer than it really needed to make. Like I just could not track down any information, and it was so unmotivating to feel like I was so lost. I finally did get the video made with some help from ChatGPT to like reword things and stuff like that so that it like flowed better, because again, it's just incoherent rambling when I started of just any information I could track down about observers and how they are used. The examples are not good examples. All the stuff in the update things that like hey, observers, that like they don't tell you really anything about how to use them, just that they exist. So this video fucking took ages. Anyway, I'd like to thank my Kofi supporter. Your monthly contributions kept reminding me that I was supposed to be working on videos when I get an email saying my Kofi supporter came in. So thank you for like sticking with me, even though like I haven't uploaded in like 2 months or something like that. So you can find a link to my Kofi in the description if you want to help support the channel. I also have YouTube memberships if you want to do that. And there's also a link to my Discord down there if you just want to come chat or tell me what I did wrong. I don't know. Anyway, for next video, I'm thinking I will do a video on any of, because it's like a really straightforward query parameter that you can provide that just like make sure that at least one of them exists, but gives you options so you don't actually necessarily know which one exists. That or the like next video, as opposed to Bevy Basics, will probably be like I want to say like maybe 5 unknown things in Bevy. So if you've got any suggestions of like really hidden features that are really cool, like at the moment I have ad hoc systems, the single system parameter, which is like a query that you call single on, but like if it fails to find a single, the system just doesn't run. So it's like a run condition and a query all done in one, and like error checking it. So it's like a really cool little like neat way of tidying code up. Anyway, I have 3, so there's 2 more slots open if you want to suggest something to go into that video. But that's all for now, and I will see you in the next video.